Welcome back to the video lecture on fluid mechanics. In the first lecture, we have discussed the introductory aspects on fluid mechanics. We have discussed about the various fluid properties, various theories used in fluid mechanics, and how it will be used in our this video course. Also, we discussed the various fundamental theories which will be applicable in the case of fluid mechanics. Also, we discussed the various flow visualization techniques used in fluid mechanics and the flow lines like streamlines, path lines and streak lines. So, today in this lecture first we will discuss about the classification of fluids. As I mentioned earlier, so the fluids can be classified according to various fluid properties, fluid behavior, or the dimensions on which we will be dealing with the fluids or the fluid problem which we are dealing. So, mainly the fluid flow can be classified according to the rheological consideration, then spatial dimensions, then dilational tensor, then motion characteristics, the temporal variations and fluid types. So, here we will discuss in detail about the various types of fluid flow according to these various aspects. So, as I mentioned earlier, the fluids can be either gases or liquids. So, the first classification of fluid flow is whether it is gaseous flow or liquid flow. So, the first classification, as you can see in this slide, say the fluid flow can be either gaseous flow or say liquid type fluids or liquid type flow. Then secondly, according to whether the fluids can be compressed or whether it cannot be compressed. So, accordingly we can classify the fluids into compressible fluids and incompressible fluids. Mainly the gases which we will be generally dealing with will be compressible in nature, and some of the liquids also may be compressible depending upon the type of the fluids, and some other liquids we can consider as incompressible, even though sometimes we can compress to a very small level, but still it can be considered as incompressible. Say for example, water is considered as incompressible, even though it's to certain, say maybe to certain level it can be compressed by applying the pressure. And then as I mentioned, say the fluid flow or fluid can be again classified, fluid flow can be classified as steady state fluid flow or transient fluid flow. So, the fluid, since it is deforming with respect to space and time. So, if the time is, say with respect to time, if there is no variation at all, then the fluid flow is said to be steady. That means there is with respect to time there is no variation of the fluid properties. The fluid properties like velocities or depth of flow, all these fluid properties are constant with respect to time, and there is no variation with respect to time. In the case of unsteady flow or transient flow, the fluid properties like velocity, pressure, then the depth, all these parameters are varying with respect to time. So, this type of fluids are called unsteady, fluid flow is called unsteady flow or transient flow. And then as we discussed earlier, the viscosity is an important parameter, important fluid property. So, accordingly whether the fluid has, the fluid flow which we are dealing with has got a viscosity, or the viscosity is negligible or there is no viscosity, then accordingly we can classify the fluids into viscous fluids or viscous flow and non-viscous flow or inviscid flow. So, according to the variation or according to the fluid has viscosity, fluid is called viscous fluid flow, and then if there is viscosity is not considered, then that kind of fluid is called non-viscous or inviscid fluid flow. Then if there is any, say circulation or any rotation aspect as far as the fluid flow is concerned, then accordingly we can classify the fluid into rotational fluid or irrotational fluid. So, in the case of rotational fluid, there can be circulations, there can be say vorticity and all other parameters, but as far as irrotational fluid is concerned, the circulation is not there or vorticity is 0. So, those kinds of fluid are called irrotational fluid or irrotational fluid flow. And then according to the space, whether we are considering 3 dimension x, y, z. So, we can classify the fluid as 3 dimension fluid flow or 2 dimension fluid flow or 1 dimension fluid flow. As all of you know, fluid flow is definitely 3 dimension in nature. You can see any type of fluid flow is 3 dimension in nature, but many times we can consider a 3 dimensional fluid flow as say 2 dimensional. Say for example, in here you can see here say a river is considered. So, when we are considering a river section like this, if you are considering say here z axis, this is say x axis, here say y axis. So, this is x, y, z axis. So, here you can see that when we consider the fluid flow with respect to this river section like this. So, x versus z, then this other longitudinal dimension is not considered. So, in this case the fluid flow can be considered as 2 dimensions, since we may be interested what is happening with respect to this x direction and z direction. Even though the fluid flow is definitely 3 dimension in nature, but say we are simplifying the 3 dimensional fluid flow into 2 dimensional, since it will be very easy to analyze and to interpret the results also it will be very easier. So, depending upon the case, depending upon the problem, depending upon the fluid flow problem, we can consider a 3 dimensional flow as 2 dimensional, so that the accuracy of the results are not much affected. And the same say the river flow we can consider in sometimes as 1 dimensional flow. Say for example, if you are considering say the river is flowing like this. So, in this case when we are dealing from say one section to another section, say here 1 1, say 2 2, 3 3. So, when we are dealing from what is happening from section 1 to section 2 and section 3. So, in this case obviously the fluid flow is 3 dimensional nature, but we can consider the flow, the what is happening with respect to this longitudinal direction is considered as far as this river flow is concerned. So, we can consider in this case the fluid flow as 1 dimension. So, all the fluid flow which we are dealing with is 3 dimensional in nature, but depending upon the problem, to simplify the problem we can consider the fluid flow as 2 dimensional or whether we can consider sometimes as 1 dimensional. So, these simplifications makes the problem analysis much simpler, the interpretation of results also much easier without losing much accuracy. So, in most of the problems, even though 3 dimensional nature, we may be solving in fluid mechanics, we may be solving as 2 dimensional fluid flow problem or 1 dimensional fluid flow problem. So, as we have seen the previous slide, so as I mentioned, the fluids can be either gases or liquids based upon the molecular behavior, as you can see in this slide. And then in the second case, the fluids, say when we are considering say a continuum or discrete fluids. So, a continuum means individual molecular properties are negligible, so that we are considering say as a continuum. So, this most of the fluid flow problems you will be considering as continuum, and in other aspects say we can also consider discrete fluids. So, in the case of discrete fluids, each molecule is treated separately, and then what is happening with respect to that molecule is studied. So, 2 aspects is there in fluid flow analysis, either a continuum analysis or discrete fluid flow analysis. Most of the time we will be dealing with the continuum fluid flow analysis, and in very rare cases we will be dealing with the discrete fluid flow analysis. And in third case, we can again say the fluids can be either perfect or ideal fluids, or the fluids can be real fluids. So, real fluids, as I mentioned earlier, does not slip past a solid wall, and most of the fluids which we are dealing with is real fluids. So, the third case is perfect versus real fluids, and the fourth cases, as I mentioned, is Newtonian versus non-Newtonian fluids. So, in the Newtonian fluids we consider the coefficient of viscosity, dynamic coefficient of viscosity mu constant, say for fixed fluid temperature, and pressure, say for example water is considered as Newtonian fluids, and then we have already seen earlier non-Newtonian fluids when the shear stress versus shear strain variation is not linear. So, those fluids are non-Newtonian fluids, and then the non-Newtonian fluids, say as I mentioned, the mu varies, say for example milk is a non-Newtonian fluid, and in the fifth case the fluid can be classified whether as compressible or incompressible fluid. As we have seen earlier, the compressible fluid, the density changes with applied pressure. If we apply some pressure to the fluid, the density changes. Say for example, if you consider just some air, then we can see in a container, if you put some pressure, say in this container some air is there, if you put some pressure, the density inside changes. So, this is what is called compressible fluid, and incompressible fluid is density will not change by external force. So, this kind of fluid is called incompressible fluid. Say for example water, when we apply some pressure, the density is not changing accordingly. So, that type of fluid is called incompressible fluid. And the sixth classification, as I mentioned, the fluids can be classified as whether steady state or unsteady. In the steady fluid flow, the properties like velocity, the pressure are independent of time, and unsteady fluid flow, the properties depend on the time. And already we have discussed the one dimensional, two dimensional, three dimensional flow, according to the spatial variations. And in the eighth classification, we have already seen the rotational versus irrotational flow. So, irrotational flow, there is no rate of angular deformation of any fluid particle. Say for example, potential flow can be considered as irrotational flow, and say rotational flow, there is a rate of angular deformation, say with respect to the fluid flow. So, these are some of the important classifications of fluids and fluid flow used in fluid mechanics, and then based upon these classifications, say the study of the fundamental principles also will be slightly varying. So, in the coming lectures we will be discussing in detail with respect to the various types of fluids, also how it will be dealing, what will be the principles used, what are the changes as far as the principles compared to the say incompressible real fluids or compressible fluids. So, that we will be discussing in later lectures. So, now finally in this introductory lecture, say we will now discuss how we can solve a fluid flow problem. So, if we get a problem, a fluid flow problem, then how we can solve. Say the problem may be, say, to find out the velocities, or the problem may be to find out the pressure distribution, or say the viscosity changes or density changes, or any type of engineering fluid flow problem. So, if we get how we can approach the problem, and then how we can solve the problem. So, these questions we will be asked generally, how we can solve the problem, what are the approaches used, and how we are getting the solution. So, here this flow chart briefly indicates how the fluid flow problem can be solved in generally. So, as far as fluid flow analysis is concerned, generally say the investigations can be two types of investigations. First one is it can be theoretical investigation, and second one is the experimental investigation. So, in theoretical investigation, what we are doing is, say based upon the available theories, based upon the say fundamental principles, or based upon the say available literature, published papers, we are trying to approach the problem, we are trying to solve it theoretically with our theoretical background. Maybe it may be some exact solutions available, or analytical solutions available, or it may be say some numerical methodologies which we can directly apply for the solution for the problem. So, this is actually a mathematical way of approach, since we are trying to solve the problem theoretically. And in the case of experimental investigation, what we are doing, we are say trying to replicate the problem in the laboratory, say to certain scale. So, there will be a scaling is to be done in the most of the real field problem will be very large in nature. We cannot replicate the same in the laboratory. So, what we can do is we can reduce the dimensions, we can use certain scale, so that the problem will be small in nature and we can easily deal in the laboratory. So, experimental investigation are very much used in fluid mechanics in the last 200 or 300 years, and experimental fluid mechanics is very much developed in the solution of various problems. So, but as far as experimental investigations are concerned, there are certain limitations. The limitations are, say, it is very expensive in nature, and then we have to make do the scaling. So, the scaling by doing the scaling, certain aspects of the problems may not be able to replicate in the laboratory. So, the reality, the certain level of the reality of the problem may be lost in this replication in the laboratory and then running the model in the laboratory. So, the accuracy may be reduced. So, experimental investigations have got its own limitations, but theoretical investigations also say if exact solutions or analytical solutions are not available, then it has got its own limitations, say the accuracy again may be reduced. So, now as far as theoretical investigations are concerned, so how we are approaching the problem, say if the engineering the fluid flow problem is given, then first we can say understand the problem, say in a physical nature, what is the problem, what are the inputs data available, what are the outputs expected, so what are the say physical principles based upon the problem which we have to investigate. So, this analysis is called the physical analysis. So, the physical analysis can be done based upon the representation of the problem given by a client, or say we can go to the real problem. Say for example, if we are constructing a bridge across a river, then say here if we are planning to construct a bridge across a river, then we have to construct pillars, and then we have to say take the say understand the flow behavior across the river section. So, that say we have to do fluid flow analysis as far as the section is concerned where the bridge is going to get constructed. So, we may have go to the field and see how the river is flowing, say what are the important parameters which we have to deal here. So, here we have to analyze, we have to understand the problem physically. So, we may have to go to the field, or we have to analyze in our office based depending upon the data available say given by the client. So, say for example, when we are going to construct a bridge across a river, so we have to see depending upon the monsoon or depending upon the rainfall throughout the year, how the water level will be varying, say whether it is how it is increasing or how it is decreasing, and then what will be the flow velocities say at the particular location where we are going to construct the bridge, and then say the bank of the river, that means the whether there is any erosion problems, or all these things we have to analyze physically. So, this is so called a physical analysis. So, in the case of fluid mechanics analysis, so this physical analysis can be based upon the force concept or energy concept. So, the force concept means, say generally we will be analyzing what are the forces acting on the particular say problem which we are dealing with, and then how it is going to affect the fluid flow properties or the particular say variable which we are going to analyze. And the second concept is called the energy concept. So, the how energy variation, say like say the energy equations we will be analyzing and how it will be affecting the particular problem. So, the physical analysis is very important in the solution of any fluid flow problem. So, physical analysis generally can be based upon the force concept or based upon the energy concept. And then after this physical analysis is over, so we can understand the problem in such a way that which way we should approach the problem, and then we can try to make a mathematical formulation of the problem. So, the after this physical analysis, next step is the mathematical analysis. In the mathematical analysis, say we will be with respect to the physical analysis. Now we already know what will be the domain of the problem which we will be dealing. Say, as I mentioned, when we are going to construct a bridge across a river, so there will be, say, where the piers will be constructed, and then what will be the flow conditions, all these things will be analyzed. So, we know the domain of the problem. So, the domain of the problem is known, and then also we can easily identify the data, like say for example, what will be the flow depth variations at various seasons, or we will say with respect to throughout the days of the year, how the flow depth will be varying. So, all these data are available. Then the boundary conditions, say like if the problem is concerned, say at particular location of the domain, say the boundary how the flow will be, the conditions like depth variations or velocity variations, that can be identified, and then say we can, based upon the particular problem, we can get the mathematical equations. The mathematical equations can be derived based upon the theoretical analysis, say either based upon the force concept or the energy concept. So, once the mathematical equations are derived, and then the boundary conditions, and boundary conditions are required for steady state problem or transient problems. But in the case of transient problem or unsteady state problem, we have to also say prescribe the initial conditions. Say at time t is equal to 0, what will be the conditions? Say maybe the depth, say velocity or pressure, or these parameters how will be varying, say at time t is equal to 0. So, from time t is equal to 0 only our transient analysis or unsteady state analysis of the fluid flow problem is starting. So, these initial conditions are very much important in fluid flow analysis, and then the governing equations are prescribed. Then we will be we have already prescribed the boundary conditions of the problem. So, with respect to this, the mathematical analysis is complete. So, again I will say briefly with respect to a figure here, I will describe the, say for example, if you consider the potential flow problems, say it can be, say flow in a homogeneous isotropic aquifer which is governed by, say del square phi is equal to 0, the Laplace equation. So, if you consider a rectangle domain like this, then we know the length, then we know the breadth. So, now the dimensions of the domain is known. So, the domain nature is known. So, now say for example, if you are dealing with the potential flow problem, so here the governing equation is del square phi is equal to 0, the Laplace equations, and then the boundary conditions, say this is a steady state problem. So, the boundary conditions can be, say here the potential. So, here the potential phi is prescribed at this boundary, say phi is equal to, say phi 1 here, say phi is equal to phi 2 here. So, the boundary conditions on this phase, say here in this domain A B C D. So, on A D the boundary conditions are, in this particular case the boundary conditions on A D phi is equal to phi 1, and similarly on B C we can prescribe phi is equal to phi 2, and now the governing equations are known, the boundary conditions are known, and on boundary A B, say for example, if we know the variation or the flux, the del phi by del n, say if it is equal to 0 here, or del phi by del n is equal to 0 on the boundary A B, and say C D here del phi by del n is equal to 0. So, that means no flow boundary condition on A B and C D. So, there cannot be, say flux cannot cross, that means this side A B and C D are impermeable in nature. So, these boundary conditions are called a natural boundary condition, that means the what is existing in the nature. So, this the flow cannot cross, this can be an impermeable boundary on this side A B and on this side C D. So, these conditions are called natural conditions or Neumann boundary conditions, and the boundary condition which is prescribed on AD and BC are called Dirichlet boundary conditions or direct boundary conditions. So, as far as this particular potential flow problem is concerned, now the mathematical analysis or mathematical statement is over, since we have already described the domain, we have already described the boundary conditions, we have already described the governing equations. So, now with respect to this we can solve this problem, either we can get an analytical solution depending upon the problem, or we can solve the problem numerically, so depending upon the case. So, this is about the mathematical analysis, and as I mentioned, in the experimental investigation is concerned, say we have to replicate the real problem in the laboratory, and then we will be with respect to certain scale, and then we will be in real terms we will be running the experiment, what is happening in the field, that will be done in the laboratory, and then we will be taking some readings. Sometimes it can be, say, either the velocity measurement or the depth variations or pressure measurement. All these measurements will be done experimentally in the laboratory, and then to have some specific relationships we can do some dimensional analysis as mentioned in the slide here. So, dimensional analysis is also very important in experimental investigation as well as mathematical investigation. So, dimensions, say with respect to like Buckingham pi theorem or various theorems, we will be discussing about this dimensional analysis later. So, in summary, in this introductory lecture on fluid mechanics, we have discussed the various aspects of fluid flow, the various fluid properties we have discussed, then we have discussed the fundamental principles which will be used in the fluid flow analysis, like the conservation of mass, conservation of momentum, conservation of energy, and then we also discussed the various fluid visualization techniques like using dyes, then using, say, smoke or other methodologies we have discussed, and then we have also discussed say various methodologies of representing fluid flow like streamlines, potential lines, streak lines, path lines we have discussed, and then finally we have discussed based upon the various fluid properties. We have classified the flows just like with respect to space, 1D flow, 2D flow, 3D flow, or with respect to the viscosity, viscous flow or non-viscous flow, and then finally we have discussed about the how we can approach a fluid flow problem or the solution to a fluid flow problem. So, as I mentioned, we can approach the fluid flow problem theoretically or experimentally, and then in theoretical investigation we can derive a mathematical model, so by describing the domain, then governing equations, boundary conditions. So, this is about the introductory lecture on this video course on fluid mechanics. So, in this second chapter on fluid mechanics video course, we will be discussing mainly fluid statics. So, the main objectives in this section are to introduce the concepts of fluid pressure, forces on solid surfaces, buoyant forces, and related theories. Then secondly, determination of fluid pressure and forces for various cases, and then we will be emphasizing the importance of fluid statics as far as fluid mechanics is concerned. Now, say as I mentioned earlier, statics fluids means fluid is not moving, that means fluid is in rest. So, you can see here there is some water in a small basin. So, here fluid is now at rest, there is no movement as far as the fluid is concerned. It is, as far as this boundary is concerned, the fluid is at rest. So, that we can say that, say now the fluid is in static conditions, and say the various theories on statics will be applicable as far as fluid flow of in static fluid is concerned. So, in solid mechanics, various theories, most of the problems we will be analyzing as in static condition. So, most of the theories in solid mechanics are applicable for fluids at rest or static fluids. So, in static fluids you can see that since fluid is not moving, it is at rest here. So, that there is no shearing force. So, since whenever there is the fluid is trying to move only, there will be between the layers there will be shearing force, but as far as a fluid at rest or static fluid, there is no shearing force. So, we do not have to worry about the shearing force is concerned. And now, before going into the more details of fluid statics, we will just review some aspects of forces and stresses. So, forces, we can classify the forces into body forces and surface forces. So, the forces can be either body forces or surface forces. The body force, it acts through a distance. Say for example, say when there is a gravitational force, the force of gravity is concerned, it is not directly acting, but it is acting from a distance. So, the action is through a distance. So, and also if you consider the electromagnetic force, most of the time it will be acting at a distance. So, the force which acting this kind of forces like gravity force, electromagnetic force acting on fluids, and that kind of study which we are dealing will be related to the body force. And the second kind of force is called the surface force. So, surface force is concerned, it is due to the virtue of direct contact between the molecules. So, what is happening as far as the fluid is concerned here? So, if you apply a force here on the fluids, so then between the due to virtue of direct contact between the fluid molecules only, there is a force. So, that force is called the surface force. And as stress is concerned, we can also classify, as we have discussed earlier, stresses as normal stresses and shear stresses. So, normal stress means when we are considering say a direct normal force on the body. So, that kind of stress is called normal stress, and when there is a shearing force is applied, that kind of stress is called shear stress. So, we will be dealing with the normal stresses and shear stresses in fluid mechanics, and also the stress can be, say, since we will be dealing with x, y, z directions. So, here this is x, this is say y, this is z. So, stress tensor. So, the stress can be, the normal stress can be say in x direction, y direction, or z direction, or with respect to x and y, with respect to x and z, or with respect to y and z. So, like that the stresses will be varying. So, say for example, if sigma is the stress, the normal stress, then the stress, if you consider a body like this, say in 3 dimension, then if you consider say x, y and z, the normal stress we will be considering, say if it is acting from say x direction, the normal stress can be sigma x, and if it is acting from the y direction, so it can be sigma y, and from the z direction it can be sigma z. And then with respect to say x y plane, if it is acting, it can be sigma x y or sigma y x, or if it is with respect to say x and z axis, then it can be sigma x z or sigma z x, and then if it is with respect to say y and z, it can be sigma y z or sigma z y. So, like that we can have stress tensor. So, with respect to x, y, z direction, we can classify the stresses say in x direction, y direction, z direction, or x z, y x y, or y z direction. So, stress tensor is very much used in many of the fluid flow analysis. So, we in a very similar way the shear stress is concerned, say for example, tau is the shear stress. So, shear stress is concerned, say if it is depending upon the problem, say if you consider again a cube of in 3D, if you consider like this, then say the shear stress also will be acting with respect to say if shear force here is applied and in the other direction another shear force is applied, so in this other phase also. So, according to this we can have the shear stress say in xy plane or say sigma yx tau yx, then tau yz or tau zy or tau xz or tau zx. So, according to the shear force acting, we can the shear stress also can be it will be varying with respect to x, y, z. So, the stress tensor, so for normal stresses and shear stresses we will be utilizing the stress tensor with respect to x, y, z directions. And then as far as force is concerned, say force will be say especially static fluid is concerned, force will be acting upon say externally mainly. So, the force between fluid and boundary, say for example, if you consider, it always acts at right angles to the boundary. So, here in this slide you can see here there is a boundary here and then say the force is acting. So, with respect to the boundary generally the force will be acting at right angle. So, you can see that in this fluid statics or the fluid at rest. So, when we are applying a force generally we will be considering it is acting at right angles and all the fluid static analysis will be accordingly. So, as I mentioned, most of the theories which have been developed in the case of solid mechanics are also applicable in the case of static fluid or fluid at rest. So, fluid element as at rest we can consider each element, say for example, in this basin the water is there, it is at rest. So, when we consider the fluid statics or static fluid, say here if you consider each element, then the fluid element should be in equilibrium, since there is no movement, the fluid is at rest. So, if there are any forces acting, then finally each fluid element should be in equilibrium. So, we can derive, say if we consider any solid, then say with respect to the solid phase, if the solid is at rest and in equilibrium, then say we can consider with respect to say for example, say this is solid and if it is at rest and if some forces are acting, then we know that if the body is in equilibrium, then in solid mechanics we use the equilibrium conditions. Say for example, if the forces in x directions, say it should be sigma fx should be equal to 0. So, this is one of the condition which you generally used in solid mechanics, and then sigma fy in the forces in y direction should be the algebraic sum should be 0, and then sigma fz should be 0. So, these three conditions as far as forces are concerned, considering the solid equilibrium, and then we consider each element in equilibrium, so that we can say that the algebraic sum of the forces in x direction is equal to 0, sigma fx is equal to 0, sigma fy is equal to 0, and sigma fz is equal to 0. So, these three equations as far as the algebraic sum of the forces sigma fx, sigma fy, sigma fz, which are used in solid mechanics, these equations the solids at rest, these equations are applicable for static fluid also, or fluid statics we can use this equation sigma fx is equal to 0, sigma fy is equal to 0, and sigma fz is equal to 0. And also in solid mechanics we know that say for a solid at rest, but in equilibrium condition, when there is a force is acting, then the sum of the moments of force about any point must be 0 as far as the particular solid is concerned. So, this equation is also very much used in fluid mechanics. So, as far as fluid at rest, if you consider the sum of the moments, say if you can apply any force and then it's the moment with respect to that force acting upon the fluid at rest, and then with respect to about any particular point, the sigma mx, that means the sum of the moments of forces should be equal to 0. So, these fundamental equations, the sigma fx is equal to 0, sigma fy is equal to 0, sigma fz is equal to 0 and sigma mx or the some moment of forces about any point must be 0. These 4 equations are very much valid in the case of static fluid also. So, these equations generally we use in solid mechanics, and directly these equations are applicable in the case of static fluid. Now, another important aspect as far as fluid statics is concerned, pressure. Pressure, as I mentioned earlier, pressure is the average of normal stresses. So, if there is a force is acting, force per area or force per unit area is the term pressure, and generally we will be considering the average of normal stresses as bulk stresses, and that term is defined as pressure. So, it is the force per unit area, and the generally used unit in system international is 1 Pascal, which is equal to Newton per meter square, and its dimension is m L to the power minus 1 and T to the power minus 2 as shown in this slide. And say for example, another unit which is called a bar is also used. 1 bar is equal to 10 to the power 5 Newton per meter square. So, this pressure is also a very important term as far as fluid statics is concerned. We will be discussing further about the pressure shortly as far as fluid statics is concerned. And another important aspect as far as fluid statics is concerned is equilibrium. Say equilibrium conditions in solid mechanics which we generally use is stable equilibrium. Say for example, this cylinder here is said to be stable if it is placed like this, so that it is stable, there is no change. It is say even if you apply small forces, it will come back to its normal position, say with respect to small forces. So, that is called a stable equilibrium. But if you consider this cylinder, if you put it in the other ways like this, then you can see even with a small force it is quite unstable. So, the solid is said to be unstable, is said to be in this position, it is said to be in unstable equilibrium. And then the third equilibrium condition used is called a neutral equilibrium. So, when it is lying like this on this floor, then it is in neutral equilibrium. So, it is say whatever force it is applied, it will be coming back to the same condition. So, it is said to be neutral equilibrium. So, equilibrium conditions, stable equilibrium, unstable equilibrium and neutral equilibrium are very much used in solid mechanics. So, these equilibrium conditions are also very much valued in the case of static fluid, which we will be discussing later. Now, we will be discussing about the fluid pressure. So, one of the important theories developed in 17th century is called Pascal law for pressure at any point. So, this law had been developed by Blaise Pascal, say by various experiments. So, here if you consider the fluid at rest, and now we are considering this slide a fluid element, and then with respect to this fluid element, Pascal observed with respect to various experiments that the pressure at any point is same in all directions. If we consider a fluid element like this, then the pressure at any point is same in all directions. Say for example, if you consider the water in this basin, say if you consider the pressure at any point in this, since the fluid is static or there is no movement, and then if you consider the pressure will be same in all directions. So, this is the law derived by Pascal. It is called Pascal's law. So, here you can see a fluid element in this slide. Here say if you consider this fluid element with respect to this phase, the force will be the pressure Py in this direction, Py into delta x into delta z on this direction, this is the force, and in the other direction, this direction it is Pz into delta x into delta y, and this direction it is say s direction which we are dealing is say Ps into delta x into delta z. So, if you consider fluid elements like this, now according to the Pascal's law, when a certain pressure is applied at any point in a fluid at rest, pressure is equally transmitted in all direction and to every other point in the fluid. So, if you consider this, say with respect to the fluid element which we have considered, sigma Fy can be written as sigma Fy is equal to Py into delta x into delta z minus Ps into delta x delta s sin theta, that is equal to rho into delta x delta y delta z by 2 into Ay, where rho is the density of the fluid and Ay is the acceleration of the fluid element which we are considering. So, here we are using the Newton's second law, the total force is equal to mass into acceleration. So, similarly, in the z direction sigma Fz is equal to Pz into delta x into delta y minus Ps into delta x into delta s cos theta minus gamma delta x delta y delta z by 2, since the weight of the element is considered in this term, that is equal to the mass into acceleration in the z direction. So, here mass is rho into delta x into delta y delta z by 2 and Az is the acceleration. So, now if you simplify the force, the sigma Fy, the total force, the algebraic force in y direction, that which is equated to the mass into acceleration, and sigma Fz which is equated to mass into acceleration in the z direction. So, if you simplify this, we will get Py minus Ps is equal to rho into y delta y by 2, since delta y can be written as delta s cos theta and delta z can be written as delta s sin theta, and then the second equation can be written as Pz minus Ps is equal to rho into Az plus gamma into delta z by 2. So, now as far as with respect to the Pascal's law, if you consider the fluid at a particular point. So, if you are considering the fluid at some particular point, then say you can see that delta x, delta y and delta z will be tending to 0. So, that we can see that Py is equal to Pz is equal to Ps as shown in this slide. So, that means the pressure at any particular point is same in all directions. So, here if you consider the pressure at a particular point at all directions, it will be same according to the Pascal's law. So, now after discussing the Pascal's law, we will be discussing the pressure variation, say at various vertical direction, horizontal directions and inclined direction, and then we will be trying to derive a general equations which can be applied in all the cases. So, if you consider as in this slide, say if you consider say the vertical element of cylinder of fluid like this. So, here say on this face the pressure is P1 and the area is A, and here the pressure is P2 and area of cross section is A, and the fluid density is rho, and from the datum if this distance is Z1 to this phase and Z2 to the second phase, the pressure decreases. You can see that the pressure decreases with the height. So, that we can in vertical direction we can write the equation P1 into A minus P2 into A minus rho g A into Z2 minus Z1, that is equal to 0. So, this gives the pressure variation in the vertical direction. So, similarly, if you consider the pressure variation in horizontal direction. So, here a horizontal fluid element, say cylinder of fluid is considered here, and the area of cross section is same A, the fluid density is rho, and on this left hand side face the pressure is P1 and it will be here on, it will be again P1 same, and say the P left multiplied by A is equal to P right A. So, since in horizontal direction on this position the total pressure, the total force is equal to this position. So, that pressure in horizontal direction is constant. So, that accordingly the pressure variation in horizontal direction is constant. So, with respect to this, if we consider the pressure intensity of fluid say for various shapes. So, you can see that with respect to in this slide the shapes are varying from here the rectangular, then here the circular, then say conical, different shapes. And now if you consider a line xs like this at a height h. So, here the fluid pressure will be same on the surface of the water, say it is Ps, and then if you consider this xs line for a fluid with a specific weight gamma, you can see that the fluid pressure intensity P is equal to gamma into H plus the fluid surface pressure Ps. So, this will be same in all this, say at all the points in this line x's. So, this gives the pressure intensity of fluid, say at this particular section x's. So, this principle we can utilize in many areas. Say now, say if you consider a piston type mechanism here. So, forces versus area. So, if we consider a small piston here and here the small cylinder here and a larger cylinder which is interconnected through a mechanism like this. So, here the pressure intensity is same at level P and Q. So, pressure intensity at same, say the level P and Q, Pp is equal to Pq. So, this is a small cylinder, here this is a large cylinder of area A2, and here area small cylinder area cross section is A1, and pressure intensity is same P at this point and at this point on the the lid of the cylinder. And then you can see that since the area of cross section A1 is smaller here and here the area of cross section is larger. So, if you apply if you get the total force F1 will be equal to P into A1 on this face here, and here it will be F2 is equal to P into A2. Since the pressure intensity is same, we can see that we can transmit a large quantity of force. So, here F2 is equal to P into A2 is much larger compared to F1. So, the transmission of pressure through stationary fluid is possible with respect to this mechanism. So, say since the pressure intensity is same and area of cross section A2 is much larger compared to A1. So, for larger area, larger force F2. So, this principle is very much applicable in many of the mechanisms like lifts, say hydraulics lifts, we will be utilizing these principles. Since the larger pressure, by applying small force here, we can transmit, we can obtain larger force here. So, that is this principle is used in lifts, hydraulic jacks, presses, etc. So, what we are doing is here we are applying a small force here F1 that will give correspondingly a large force output will be, input will be small and large force output is produced here, which is used in lifts, hydraulic jacks, presses and many other hydraulic equipments. So, this principle is very much very important in fluid statics, which is based upon this theory that the transmission of pressure through stationary fluid.